Hello everyone. Welcome to your own channel, Theoretical Condensed Matter Physics. Today in this video, we are starting a new lecture series in which we will show you how to practically execute density functional theory. Okay, let's at first discuss the steps that you have to go through while performing a density functional theory calculation. The very first step will be the convergence test. In this step, you actually measure the convergence of several different parameters, which we are going to be discussing in this and in future lectures of this series. Okay, once the convergence is confirmed, then you will have to relax the structure to get the atomic coordinates that are going to be used for further calculations. Once the structure is relaxed, you have the coordinates already, then you will have to perform a self-consistent field calculation, or SCF calculation it is called. Actually, for most of the physical parameters, the self-consistent field calculation is a start. You have to do it. Once your self-consistent field calculation is performed, you can move on to calculate other physical properties. Okay. These properties may include dielectric constant, band structure, etc. Okay. Here, in this particular series, we will understand the practical execution of DFT using Quantum Espresso, which is very popular, and this particular DFT package has produced many important research papers. Moreover, this is free actually. And when you are running short in fund, this could be an excellent choice for you. So, this is our first lecture of this series of DFT practical classes, and in this video we are going to understand the Quantum Espresso input file. Okay. The simplest input file of Quantum Espresso has basically 6 sections. These are and control, and system, and electrons, K points, atomic species, and atomic coordinates. Okay, these are just 6 sections. So in your input file, these 6 sections will be there. If you are totally new to Quantum Espresso, you can think it like these are the different paragraphs. So you are writing an essay. Let's say your input file is an essay, and your 6 different paragraphs will be these. Okay. Among these 6 major sections, these 3 which start with an AND symbol are called name lists, and they always end with a slash. Okay. There are several different name lists also, which we have not shown here because at first we really don't want to make the things complicated, and we want you to understand the simplest input file at first and not bother with complication. Okay. However, just know that all the name cards will always start with an AND symbol and ends with a slash. So it's like each paragraph will start with a point. The point might be AND control or AND system, and in your essay you end each paragraph with a full stop, right? So here we will end each part of the input file with a slash. Once the slash is put, after that, whatever I may write, it will not be under that name list. Okay. Maybe I am being too tough and this may look very much complicated to you. So, but just don't run away because I am going to make them easier for you. Okay, as we move forward in this lecture. And of course, we are going to perform the examples easy and later on some advanced examples also in this lecture series. Okay. Let's first see what is there in the name card AND control. AND control is the section of the input file where we find the general and most important variables which are going to control the run. In other words, you can say that AND control is the administrator of the whole input file. Okay, and every other section will perform according to this section. Well, under a name list, there are many cards. It's like under a particular paragraph, under a particular point, there are several different sentences, right? Similarly, here in your Quantum Espresso input file, under every name list, you have many cards, okay? The first card that we are going to learn is calculation card. Here, you actually have to define the type of calculation that you are going to perform. There are several options here. For example, SCF. This means that the code will execute a self-consistent calculation. This is the basic one. No matter which physical property you want to calculate, you will have to do one self-consistent calculation at first. Okay. Next comes NSCF. This is non-self-consistent field calculation. This is needed for density of states or band structure calculation. But be aware, before NSCF, you must do a SCF calculation. Otherwise, you will get physically wrong and meaningless outputs actually. Then comes bands. This option is used for calculating electronic band structure. Relax. This is to be done even before SCF. Remember, we talked about the structure optimization at first. So that is done here. Now, under relax option, your cell parameters will remain constant, but the atomic positions will change, okay, to relax the structure. A better option for structure optimization is VC relax or variable shell relaxation. Here, both the atomic coordinate and the cell parameter will vary to see which is the lowest energy state of your system. MD. This is used for molecular dynamics calculation. And then comes VCMD. Here also we calculate molecular dynamics but with a variable shell. Okay, fine. Now don't get stressed. As a newbie, you are allowed to forget some of these. We will be using these terms so many times in this series that at the end, everything will become a matter of daily life to you. So let's put calculation equal to SCF. That's how you write a particular card. Our next card is pseudo directory. We write the pseudo potential directory as pseudo _dir. Here we actually tell the code where the pseudo potential files are kept. Here you have only two options. One is the direct path to the directory of pseudo potentials. Then it will look like this: home/example/pseudo. Maybe, and in your computer it might be different also. Another option is you may just put a dot within quotations. This means that the pseudo potential files are kept in the same directory where the original input file is. Okay. Initially, the last option will be good for you. These are called cards. There are several other cards also under control name list. But I actually don't want to scare you with so many terminologies. So for the time being, let's stay with these two cards under the control name list. But our job is not done yet. We have to tell the code that the control name list is complete, and we will do this by putting a slash. Now after this slash, whatever you are writing will not be under control name list. Next, we go to the system name list. It is written as and system. This contains the input variables of the system that we are going to study. First card under this system is iBrav. This actually means identity of Bravais lattice. So here you are actually going to define the Bravais lattice you are using. To each kind of Bravais lattice, one particular number is assigned. For example, if you say iBrav equal to 1, then the code will understand that your lattice is simple cubic. There are several others too, of course. As you know, the 14 Bravais lattices are there. So let me provide you the list of which number defines which Bravais lattice. Okay, here is the list that you are going to need. 0 is for free, but initially don't use this, as using this will compel us to change some other parameters, and this also takes longer time in relax calculations, remember. However, others are simple. As we have already said, 1 is for simple cubic, 2 for face-centered cubic, 3 is for BCC, 4 is for hexagonal and trigonal simple, 5 is for trigonal R, where 1 3-fold axis is present also. 6 is for simple tetragonal and 7 is for body center tetragonal. Okay. 8 is for simple orthorhombic, 9 for base centered orthorhombic, 10 for face centered orthorhombic, 11 for body centered orthorhombic, 12 for simple monoclinic, 13 for base centered monoclinic, and 14 for triclinic. So you may take a screenshot of this or whatever is convenient for you. Now once your Bravais lattice is defined, then comes the Cardup lattice parameter. There are different ways to write the lattice parameters, but let's learn one in this class. So A equal to, here you actually have to put the lattice parameter in angstrom unit. Remember, do not repeat same length again and again. What I am actually trying to say is, for example, if you have a cubic lattice, your A, B and C are the same. So you don't have to say all these. But for cubic, mention only A. Because in your eyebrow, it is already defined that your lattice is cubic. Okay. You don't even have to mention the angles, as the angles are already specified when you have chosen the option for eyebrow. For tetragonal, you have to mention only A and B, as A and B are not the same here. For hexagonal, you have to mention A and C. The 120-degree angle is mentioned in eyebrow by default if you have chosen hexagonal. For orthorhombic, you have to mention all the three lengths A, B and C. For trigonal, mention only A and gamma. That is the lattice parameter and only one angle. For monoclinic, you have to mention only A, B, C and one angle. The code will understand the angle by gamma here. As you can guess, only one crystal structure is left. And this is actually the bad one, and this is triclinic. Here you have to mention everything. A, B, C and alpha, beta, gamma. All. Everything you have to mention. You know why. Okay. So let's put A equal to 2.85. Next comes NAT. Here we provide number of atoms in the supercell. Next, NTYP. This is N type. Provide how many types of atoms are present in the supercell. For example, if you are using NaCl, it will be 2. That is, you have 2 types of atoms. One is Na, sodium, and another is chlorine, that is Cl. Next comes ECAT WFC and ECAT rho. ECAT WFC is actually the energy cutoff for wave functions in Rydberg unit, which essentially determines how broad your functions will be. And ECAT rho is the energy cutoff for charge density. This is also in Rydberg unit. Generally, ECAT rho is a multiple of ECAT WFC. For non-metal, it is 8 times, and for metals, it is 12 times of ECAT WFC. It's just a conventional rule. If this cutoff thing is seeming new to you, you may refer to this lecture in which we have elaborately discussed what is energy cutoff and several other things. Then comes smearing. This determines the smearing method that is going to be adopted by the code for doing the Brillouin zone integration. Options that you have here are Gaussian, Matheson-Paxton or MP, Marjorie-Van der Waals or Cold, and Fermi-Dirac or FD. Now if you don't know what smearing actually is, you may check this video in the link. Now let's fill the options, let's complete the cards to provide you a glance of how input file looks. So we will put NAT equal to 2, NType equal to 1, ECAT WFC equal to 50, ECAT rho equal to 400, that is 8 times of ECAT WFC, and smearing equal to FD. Well, and finally we have to end the AND system name list with a slash. Now of course there are several other cards under this system name list, and this is the longest chain of options, but don't worry, the options that I have described will be enough for you at first. In time, as we move on in our next example videos and maybe in the advanced ones, we are going to learn other terminologies. Now, after AND system, we have another name list called AND electrons. Here, we actually provide the details of electronic calculations. That is, the details of the self-consistent field calculation. The first card under this particular name list is electron max step. Here, we actually provide the maximum number of iterations to be performed in one SCF calculation. Now, 100 is the general convention, but I personally suggest to take it as 200, especially for VC relux calculations. Otherwise, you may get difficulties because if your convergence is not achieved in 100 steps, then Quantum Espresso is going to terminate the calculation anyway. So now that is bad for you because one calculation may take 5 days or 6 days or longer times also, depending upon your computational facility. Okay, so 200 is a safe side. Okay, so I take it as 200. Now, after that comes convergence threshold. We write it as CONV_THR. This is actually your desired accuracy. In our previous option, we have defined how many steps will be there to reach the convergence. Now here we are actually defining when the code will understand that the calculation is converged. So that is the desired accuracy. For example, if you put it as 0.000001, this is actually the default and suggested also, self-consistent field iterations will end after reaching this level of accuracy. After this comes the starting pot. This is not the starting point, remember. This is actually the starting potential. Here you have different options like atomic. If you choose this, then the code will take the superposition of atomic charges as a starting potential. Another option is file. Then the starting potential will be taken from existing charge density.xml file in the specified directory. Then you will also have to specify the path to the directory. At first, the starting point atomic will be better for you. Okay, so let's fill the cards. Let's complete the cards here. So let's take electron max step equal to 100, convergence threshold equal to 0.000001, and starting potential equals to atomic. Okay, now let's end this card by using the slash. Now after this comes k points. This is not a name list, okay, but this is a particular point under which you have to define the coordinates and weightages of the k points that are going to be used for the Brillouin integration. Now there are different formats of putting the k points depending upon what calculation you are doing. For self-consistent field calculation, the k point format will be automatic. For example, it will be 8, 8, 8. So then 8 points will be used along kx direction, 8 along ky, and 8 other along kz direction. Now, if you are calculating the band structure, then your k point format will be crystal B. One example is given here. We are adding 5 at first. That means we are taking 5 different points here. It could be gamma, k, x, s, different points are there, you know. And these are actually the coordinates of these 5 different k points in reciprocal space. And this 40, these are actually the preciseness. That is, between two particular k points, how many points will be generated. So 40 point will be generated within the vicinity of this particular k point. And everywhere we have put it as 40. 40 is a good option also for calculating the band structure. Now, if you are thinking that this k point thing is going to be difficult for me, then I suggest you to take a look at this particular video where I have explained that how many k points you need to take and several other things. Now, once the k points are defined, then comes atomic species. Here, we actually are going to provide the name, atomic mass, and the name of the pseudopotential that is used for each atomic species that are present in the system. For example, it is written as atomic species. Now, if we are using iron, then we will write Fe after a space, we are going to write 55.84500. That is the atomic mass of iron, and then the name of the pseudopotential. Now, don't worry how to find these pseudopotentials. This name looks too much complicated. Now, you actually don't have to worry about this particular thing, because after this particular video, we are going to provide a hands-on example to you. Okay, so please don't get tensed, and know that these are actually the easy calculations. Once you see the example in my next video, it will be totally clear to you. And if you want to understand what are the pseudopotentials, then you can check this particular video. Okay. After atomic species comes atomic positions. From the name itself, it is clear to you that here you have to provide the type and coordinates of each atom in the supercell. For example, we are going to write it as atomic positions in second bracket angstrom, that is, the atomic positions will be defined in angstrom unit. There are several other options also, which we are going to see in the examples. Okay, so in my particular unit cell, there might be 2 irons, right? So coordinate of one iron is that, and coordinate of another iron atom is this. Okay, so this is how you actually define the atomic positions. Another option to define the atomic positions is crystal. For relaxation calculations, this particular format is very useful. Actually, make it a rule for yourself that whenever you are going to perform the relax calculation, you are going to use the crystal units. Then you will have to define the atomic positions as a multiple of the unit lengths. Okay, like if we are using crystal units, then our coordinates will be like this. That is 0.000 and 0.5, 0.5, 0.5, or it could be this also, whatever. After relax calculation, it's going to be fine anyway. Okay. Now, one question that I get a lot is, which is better for calculation, Windows or Linux? Now, for this particular question, my answer will be, at least at first, as a newbie, don't change your operating system for the sake of Quantum Espresso, because you actually have to learn Quantum Espresso. You don't have to learn a new operating system. Okay, and of course in Linux there are some advantages. Now Windows is also very good, and now you also can do the parallel calculations using Windows. There are different softwares also for Windows. Okay, now input and output file structures are same for both Windows and Linux. In Windows, we run the commands by, for example, pw less than input file name, whatever your input file name is, .in greater than output file name .out. Okay, and this is for SCF calculation. And for band structure calculation, we will write bands less than input file name .in greater than output file name .out. In Linux, we run the commands by pw.x, that is one .x is there only, and bands.x less than input file name .in greater than output file name .out. That is it. Now my suggestion will be, don't change your operating system for the sake of Quantum Espresso. Again, I am saying this. Okay, I will show examples in Windows at first, because most of the people, most of the newbies in Quantum Espresso are Windows user in general. And also I am going to provide the videos for Linux users. Okay, so both will be provided in my channel. Okay, so stay tuned for next videos, and please share, subscribe and like this video. Thank you. Thanks a lot.